Hello everyone and welcome to lecture. Today's lecture will be about a different way of solving optimization problems with constraints or constrained optimization problems. So one of the issues that we saw when we were going over our general optimization problems was that when we look on the boundary, this becomes a problem of going through and really kind of piecing together what the maximum and min is on the boundary, or when we have a constraint. So one of the big tools that we have at our disposal is another means of doing this exact thing, of dealing with a constrained optimization problem. And this is called the method of Lagrange multipliers. Or the Lagrange multiplier method. And really, this is a very, very convenient method of essentially taking a constrained optimization problem and turning it into an unconstrained optimization problem. So the idea here is that our main problem with the Lagrange multiplier method is that we will try to maximize some multivariable function subject to one or possibly even more constraints, depending on how many number of variables we have. The big application for us is that this method allows us to solve for max and min only on the boundary of a given function or of a given domain. Which was step B in our optimization procedure that we described in the last lecture. So what we'll focus on in this lecture is just maximizing a function of two variables or I guess we should probably say optimize instead of maximize, because really this procedure will give us both the maximum and the minimum. So we'll say maximize slash minimize a function of two variables subject to a constraint. Specifically, we'll say the constraint is going to take the form of a level curve. It'll say that we have some multivariable function g of xy is equal to c is our constraint. So essentially what this is saying for a 2D function, as this is in 2D, a picture that we can kind of draw here is that we'll have our 2D function and this 2D function maybe has level curves that can be relatively complicated. Maybe it looks like this. This corresponds to a specific level of the function where maybe there's a max or a min right here. And same thing right here. So these are just level curves of our multivariable function f of xy in red. Then we have some curve, some constraint curve c. And this black curve is the curve g of xy is equal to c. So the question then is, what is the maximum of the function f subject to this constraint? That's what we're trying to ask here and trying to answer using this method. In other words, if you only move on this curve, the black curve here, g of xy equals c, what's the largest value of the function on this curve and only on the curve? If you just stay on the curve and you only consider points on the curve. This is exactly what this method will answer for us. So that when we have a problem like this is called a constrained optimization problem. Because we're trying to optimize the function f subject to the constraint, or taking into account the constraint. Now, we already know how to solve an unconstrained optimization problem, so an optimization problem without a constraint at all. And the key trick in this method, the Lagrange multiplier method, is to turn our constrained optimization problem into an unconstrained optimization problem by introducing a new variable. This new variable we call a Lagrange multiplier. So what we're going to do, and what we do here, is we transform the constrained optimization problem into an unconstrained optimization problem. Which we know how to solve. You just find the critical points and verify that those critical points are in fact global maximums of the function, this new unconstrained optimization function. And we do that by introducing what's called a Lagrange multiplier, which is a new variable. And a new function that we call the Lagrange function. These are the two big new introductions that we have to make to do this. And for this problem that we're considering now, a function of two variables with one constraint, the Lagrange function is going to be a function of three variables, or the two original variables, and of a new thing that we'll call the Lagrange multiplier. We'll call it lambda. So lambda here is the new Lagrange multiplier. And this is constructed relatively simply. We just say it's going to be the original function, lowercase f of xy, minus the Lagrange multiplier times the constraint function minus c. Because you'll recall that the constraint function, if we have a g of xy equals c, this is the same as the equation g of xy minus c is equal to 0. So you'll see why this is important in one moment. So for this new function, we want to think about how to optimize the new function. So how to optimize the function capital F. And you'll remember from our previous procedure, the first step is to solve for all critical points of capital F. And this is going to be critical points of either type 1 or type 2. We're going to only focus on critical points, or on functions f which have critical points of type 1, because it makes the analysis a little bit simpler. But you'll recall that in order to do this, to solve for the critical points of capital F, the gradient of capital F has to be equal to the 0 vector. And these are all critical points of type 1 that we classified earlier. So any point with a gradient of capital F is equal to 0 vector is a critical point of type 1. Well, this is the same thing as having the x partial derivative of f be equal to 0, the y partial derivative of capital F be equal to 0. Then because f is a function of 3 variables, it also means that the partial derivative of f with respect to lambda also has to equal 0, because capital F is a function of those 3 variables. And this gives us a system of 3 equations that each have to hold at any critical point of this new Lagrange function, capital F. And it turns out that these 3 equations have actually a lot of geometric significance. What this is saying for us is it's saying that if we take the x partial derivative of this function right here, this is the same thing as, well, the x partial derivative of a lowercase f minus lambda times the x partial derivative of g It's important to denote here that this capital F is, this gradient means the f partial derivative of x with respect to x, the f partial derivative with respect to y, and the f partial derivative with respect to lambda, because this is a function of 3 variables. So we have that this has to be equal to 0. And similarly, when you take the y partial derivative, you have that the y partial derivative of this expression has to be the y partial derivative of lowercase f minus lambda times the x, or the y partial derivative of g has to also be equal to 0. And then lastly, when we take the lambda partial derivative of this expression right here, we get that negative g of xy minus c has to be equal to 0. So what this is showing you is that any local minimum of the function capital F, of the Lagrange function, has to satisfy equation 1, equation 2, and equation 3. And what that's meaning for us, we will take a look at equation 3 first. Right? Equation 3 being satisfied means that at any local minimum of the Lagrange function, if g of xy minus c has to be equal to 0, then g of xy has to be equal to c, which means that the constraint is satisfied. This is the first big point here, that the constraint has to be satisfied at any local minimum of the function capital F. And what that means is that if we have some local minimum, let's say we have some local minimum, we'll say x star, so some solution to these three equations, local minimum or local maximum. So x star, we'll call it y star, and lambda star. Then also, if you look at the Lagrange function, the value of the Lagrange function at this critical point of capital F is going to be equal to the value of f, lowercase f, just at x star, y star. Because if equation 3 is satisfied, that means that g of xy minus c is 0. So at that point, this term is going to be 0. So the constraint is going to be satisfied, which means that x star, y star, lambda star could be a saddle point of the Lagrange function. But if it's a local max or a local min of the saddle function, then it's like if f is maximized or minimized, then so is the function f, lowercase f. The constraint is also satisfied. So this is really a big thing. This is the power of the Lagrange multiplier method, is that the maximum and minimum of capital F directly correspond to maximum and minimum of lowercase f, while also satisfying our constraint. So this is a very cool and very neat trick mathematically. We can also interpret equations 1 and equations 2 together as follows. This is saying that the derivative of f, partial derivative of f with respect to x, and the partial derivative of f with respect to y have to be equal to lambda times the x partial derivative of g and the y partial derivative of g in vector form. Well, this is an equation that's directly telling us that the two-dimensional gradient of the function f, the gradient vector of the function f in 2D, has to be equal to a constant lambda, that Lagrange multiplier constant, multiplied by the gradient of g, our constraint function. So the equations 1 and 2 are telling us actually geometrically how to go through and solve for these optimum points. That at any point where the gradient is a constant multiple, so pointing in the same direction, the gradient of lowercase f is a constant multiple of the gradient of g, you have a maximum or a minimum on that boundary point, or on that constraint point. And very often we can use this graphically to automatically determine very quickly where the potential local mins and maxes are. So for instance, if we look at this picture right here, you see that there's only a couple spots where the gradient vector of g and the gradient vector of f are pointing in the same direction. Right here, this is an example of a point where the gradient of g is pointing in the same direction as the gradient of f. So this is a potential local max or min of our function right here, because the gradient at that point and the gradient of the constraint at that point is pointing in the same direction as the gradient of g. If you look around the boundary, there's another point right here, it looks like, where those two gradients are going to point in the same direction. Right here looks like one, and right here as well. So those are all potential max and mins on the boundary, because the gradient of the constraint function is pointing in the same direction as the gradient of the function we're trying to maximize. So let's see this and how to do this for a couple of different examples, and we'll see that this is a very, very powerful method for optimization. So what we'll do here is pull in the example that we started with and we used in the optimization lecture to show that this is a new method that's giving us the exact same answers that we got before. This is the example of maximizing and minimizing the function f of xy is equal to x times y on the boundary of an ellipse, or on the ellipse x over 3 squared plus y over 2 squared is equal to 1. So we have a function that we're trying to maximize, and we have our constraint, which is that this function g of xy is equal to 1. That's the curve given by the ellipse. And like I mentioned before, if you draw the level curves of a function correctly, you can directly, many times, just kind of tell what the solution is going to give you before you even go through and do the actual math on it. So let's do that and just show that we can kind of see where the maximum and minimum of the function are going to be without even using and going through and doing this procedure. So first we'll draw the ellipse curve. It's going to look like this, roughly speaking. This is the equation g of xy is equal to 1. And then we'll also draw the level curves of this function, which are going to correspond to the following. At 1, this function is 1, 1, this function is 1, 1. At 2, 1, this function is 1 half. And at 1 half, 2, this function is 1. We have the same story down here for -1, -1. So this corresponds to the level curve c equals 1. C equals 1. At c equals 0, you have a level curve that looks like this on both the axes. And for c equals -1, you have a hyperbola that looks like this, and then same thing on the opposite side as well. And you can draw more level curves for higher and higher values of c. And you're just going to get hyperbolas for larger values of c that are sort of stretched out a little bit more. So you should hopefully be able to see that the gradient of this ellipse, of this level curve for g, is going to be pointing at these varied points perpendicular when you're at a 45-degree angle in either for any one of the quadrants, and as well the gradient of the function f at that point will also be perpendicular. So in orange here I've drawn out what the gradient of f looks like, and then the gradient of g will always be pointing out. And it's at those 4 points where the gradient vectors of each of these two curves point in the same direction. So without even doing the mathematics out on this, and going through and actually solving the system of equations that we get, equation 1, equation 2, equation 3, we have that we can identify with just the level curves and the constraint curve where the potential max and mins of our function are on this boundary, on this constraint curve. And if you remember from the previous lecture, those are the 4 points that we solve for. So those are the correct locations of the max and mins. And so what we want to do is go through and actually do the procedure and show that it actually works very well. And we can go through and solve the system of equations that we get with the Lagrange function. So the first thing that we need to do with this procedure is set our Lagrange function. And this is going to be the function that we're optimizing, which is x times y minus lambda times our g function, which is x over 3 squared plus y over 2 squared minus c, or minus 1. So this right here is the correct Lagrange function for this problem. Once the Lagrange function is set, then we can go through and follow our optimization procedure for this Lagrange function. So what that involves is solving for the critical points of the Lagrange function. which will give us equation 1, which is that the x partial derivative of capital F should be equal to 0. The x partial derivative of capital F is going to be y minus, and then when you go through and compute the derivative with respect to x of this expression right here, you're going to get 2 lambda x over 9. And there's no more x variables up here, so this is it right here. This is our equation 1. This is the partial derivative of capital F, the Lagrange function. Now it turns out that this is going to be a little bit more convenient to write in the form y is equal to 2 lambda x over 9 because ultimately we're going to plug this into the constraint function, so we should also square this as well. Get y squared is equal to 4 over 81 times lambda squared x squared. So these are equivalent notations for, or equivalent representations of this expression right here. Equation 2 is saying that the y partial derivative of the Lagrange function at any critical point has to be equal to 0. And the y partial derivative of our Lagrange function is going to be x minus lambda times y over 2. When you go through and take the partial derivative of this right here, this is exactly what you'll get. And again, rewriting this in the form x equals lambda y over 2, or x squared is equal to 1/4 times lambda squared y squared, will be convenient for us when we plug into equation 3. And so the last equation that we have when we optimize or look for the critical points of capital F, our Lagrange function, is going to be equation 3. Or our constraint equation is saying that the lambda derivative of f has to be equal to 0. And this is going to be negative times x over 3 squared plus y over 2 squared minus 1 has to be equal to 0, which is just the equation of our constraint, or x over 3 squared plus y over 2 squared is going to be equal to 1. So the main idea here now is that we have 3 equations, we have 3 unknowns, and if I can solve this system of equations for our unknowns, x, y, and lambda, we hopefully have solved for any and all possible solutions to our optimization problem. And it turns out that this is going to give us exactly the 4 solutions that we found the other day using the parameterization method for optimization on a boundary. So we'll start by considering and trying to eliminate variables by plugging equation 1 into equation 3. So if we take equation 3 and we plug equation 1 into equation 3, equation 3, remember, I'll just write that right here so we can see directly what we're plugging into. Equation 3 is the equation x squared over 9 plus y squared over 4 is equal to 1. And if we plug in for y here, we get x squared over 9 plus y squared, which is 4 over 81 times lambda squared x squared over 4 is equal to 1. When we divide by 4 here, the 4's cancel out. And I can also factor out an x squared to get the equation that x squared, you can factor out a 9 as well, x squared over 9 times 1 plus lambda squared over 9 is equal to 1, or x squared over 9 is equal to 1 over 1 plus lambda squared over 9. So this is, plugging equation 1 into equation 3 eliminates y and just gives us a dependence of x on lambda. It tells us how x depends on lambda. We want to do the same thing for equation 2 and equation 3. That is, plug equation 2 into this expression for equation 3, and the idea is that this is actually going to eliminate x for us in this equation. So when I do that, I plug in for x squared. X squared is lambda squared times y squared over 4 from before. If you remember from before, we ended up finding that x squared was 1/4 lambda squared times y squared from equation 2. So we plug it into equation 3 to get x squared over 9 plus y squared over 4 is equal to 1, which is the same if I factor out this y squared over 4 as the equation y squared over 4 times 1 plus lambda squared over 9 is equal to 1, or lastly that y squared over 4 is equal to 1 over 1 plus lambda squared over 9. So we've solved for the relationship between x squared and lambda, or between x and lambda. We solved for the relationship between y and lambda. The last thing to do is to eliminate both variables x and y. So plug this expression and this expression into our equation 3 and isolate lambda, thereby solving for lambda. We get one equation that we can solve for lambda. So we're going to take both of those two results and plug into equation 3. Remember, equation 3 is x squared over 9 plus y squared over 4 is equal to 1. And we've solved for x squared over 9 and y squared over 4. They're the same thing. X squared over 9 is 1 over 1 plus lambda squared over 9. And y squared over 4 is also 1 over 1 plus lambda squared over 9. Which gives us the equation 2 over 1 plus lambda squared over 9 is equal to 1, or 2 is equal to 1 plus lambda squared over 9, or 1 is equal to lambda squared over 9, which means that lambda squared is equal to 9. So lambda is equal to plus or minus the square root of 9, which means that lambda is equal to plus or minus 3. So the two Lagrange multipliers that work for this problem are plus and minus 3. Not only that, we can actually go through and now that we have our two possible values of lambda, and actually solve and use this in our equations, our previous two equations. So from our previous two equations, we take this result and we plug back in from our first equation. We can call these two equations, if you want, equation 1 star and equation 2 star, just for labeling purposes. So this last step was taking equation 1 star and equation 2 star and plugging them into equation 3 to solve for lambda, to kind of eliminate both variables x and y. If we now take another look at equation 1 star gives us x squared over 9 is equal to 1 over 1 plus lambda squared over 9. And if lambda is plus or minus 3, then that squared is going to be equal to 9. So x squared is going to be 1 over 1 plus 9 over 9, which is 1, or 1/2. Which means that x squared is going to be 9 over 2 if I multiply both sides of this expression by 9, or x is going to be plus or minus the square root of 9 over the square root of 2, which is plus or minus 3 over the square root of 2. Likewise, we can do this for equation 2 star. And remember, equation 2 star is giving us that y squared over 4 is equal to 1 over 1 plus lambda squared over 9, which is 1 over 1 plus 1 when you plug in plus or minus 3, or 1/2. So that gives you that when you plug back in, or when you first will solve for y squared is equal to 4 times 1/2, or 4 over 2, which means that y is equal to plus or minus 2 over the square root of 2 when you take the square root of both sides. And what this gives us then is exactly the same solutions that we found with the previous method. They're the directly, the same solutions that we found using the parameterization method for the boundary, but it's with an entirely new method of calculating this optimization, the solution to this constrained optimization problem. And this is really incredible. There are two methods of doing this, and this method of solving a constrained optimization problem is very, very powerful. It can be applied in a wide variety of scenarios, and using many different kind of tools in some sense. So I guess what I'm trying to say is that this is what I've shown is only for a function of two variables and a constraint with two variables, but this idea extends to a wide variety of problems. Optimizing a function of say 5 variables with 2 constraints. All of these methods can be directly extended, which is very, very incredible. And what's amazing is that using this method, if you use the Lagrange multiplier method, right, you can get a nice graphical depiction of exactly where the max and mins of the functions are, of a given function are, with a constraint on a constrained optimization problem. And you can see very clearly in this picture that we're able to draw a picture of the level curves and the constraint function and immediately tell where the max and min values are going to be on this constraint curve without even going through and doing this procedure, which is sometimes a little bit long, but you can see very clearly that it produces the correct answer, both for the points, the x and y values that are the max and the min on the constraint curve, and also for the Lagrange multiplier, which is in some sense a constant of proportionality between the gradient vector at a point and the gradient of the constraint at a point. So the last problem that I want to look at for an example of this procedure is a slightly more applied problem, and this is the following. Let's say we have some sort of cost function, and we also have a production constraint. So let's say we're producing a certain let's say we're producing two things. We'll call them devices just to be, very specific. X is the amount of device 1, and Y is the amount of device 2. And specifically, we have a production constraint, so it's subject to it says that the maximum total amount, or combined total of these items, these devices, is equal to some value. We'll just say 60 for argument's sake. So that means that x plus y is equal to 60. Well, we can go through and directly apply our Lagrange method. We'll also suppose, for argument's purposes, that c of xy is the cost function for producing x and y. Now this can take a lot of different forms in general, but for argument's purposes we'll just go through and say it's some sort of quadratic function of x and y. say for certain reasons it's going to be 5x squared plus x times y plus 2y squared plus 500. So for any amount of the quantities x and y, this function is giving us the exact cost of production. Maybe it costs a little bit more to produce a certain x amount of x versus a certain amount of y. So this coefficient of x squared is bigger than this 2 right here. But you can think of this cost function as being the exact function, mathematical function, that gives us the exact amount that it costs to produce a certain amount of units x and y. So we have this is directly a Lagrange multiplier, or I should say it's a constrained optimization problem that is directly in the form for application of Lagrange multiplier method. And that's because directly we can construct our Lagrange function, which is going to be capital F of xy and lambda which is 5x squared plus xy plus 2y squared. It's the function that we're optimizing, and that'll be minus lambda times the constraint function, which is x plus y minus 60. Because our function lowercase f of xy that we're optimizing is this cost function. We want to find the optimal cost, right? When we have this constraint right here. So this is our constraint function, g of xy. So our Lagrange function will take this form right here, where this is our f of xy minus lambda times g of xy minus c. So going through and applying our procedure, we have our 3 equations that have to be true at any critical point of f. The first is that the partial derivative of f with respect to x has to be equal to 0. And when we take the partial derivative of this with respect to x, we get the equation 10x plus y minus lambda is equal to 0. Or y is equal to lambda minus 10x. Equation 2 is that the y partial derivative of our Lagrange function has to be equal to 0. This is going to tell us that x plus 4y minus lambda has to be equal to 0, which is the same thing as the equation x is equal to lambda minus 4y. And then lastly, equation 3 says that the lambda partial derivative of our Lagrange function has to be equal to 0, or negative x plus y minus 60 has to be equal to 0, which is just saying that the constraint has to be satisfied. So we have 3 equations for 3 variables, And it turns out this is actually a nice system because it's a linear system of equations. So it's a little bit easier to solve than the previous example problem. But I wanted to go through both to show you that it's possible to do even in more complicated scenarios. The first step is to combine equation 1 and equation 3. We'll use our elimination procedure from before. In general, there's multiple different ways of going through and solving a system of equations, but typically I think that elimination is the most straightforward method of doing it without any linear algebra background. Now with linear algebra, you can deal with very large systems of linear equations, but the idea here is that we'll kind of just stick to one of the most straightforward methods here, which is elimination. So I'll take equation 1 and equation 3. If I plug equation 1 into equation 3, I get the equation x plus lambda minus 10x is equal to 60, which is the same thing as the equation negative 9x plus lambda is equal to 60. Or x, if we solve this equation for x, is equal to lambda minus 60 over 9. This is, we've eliminated y, so we'll call this our equation 1 star. In a similar manner, we can go through and combine equation 2 and equation 3. And this is going to give us the equation, when we plug in for y into this equation from equation 2, or plug in for x, we plug equation 2 into equation 3, we'll get lambda minus 4y plus y is equal to 60, which is the same thing as lambda minus 3y is equal to 60, which we can solve for y to get that y is equal to lambda minus 60 over 3. And so we have from equation 1 and equation 3 the relationship between lambda, the Lagrange multiplier, and x. When we do equation 2 and equation 3, we get an isolated equation relating y and lambda. The last step here is to go through and combine these. So we combine this equation 1 star with this equation 2 star, just like we did in the previous problem. So from equation 3, is that x plus y equals 60. So x is lambda minus 60 over 9 plus lambda minus 60 over 3 is equal to 60. So this gives us an equation that we can actually isolate for lambda, and we can directly solve for lambda here. So if we go through and do this, I think that the easiest thing to do is probably multiply both sides by 9. That will give us the equation lambda minus 60 plus 3 lambda minus 3 times 60 so 3 times 60 then is equal to 9 times 60, or the equation 4 lambda minus 4 times 60 is equal to 9 times 60. Which is the same thing as the equation 4 times lambda minus 60 is equal to 9 times 60. Which is the same thing as lambda minus 60 is equal to 9 times 60 over 4, which is 9 times 15, or 135. So lambda is equal to 60 plus 135, or 195. So our Lagrange multiplier for this problem is 195. And then the last step of the problem, I'll add one more page here so we can go through the last step of the problem, which is to take this and directly plug in for x and for y. So we have that x is equal to lambda minus 60 over 9. This is going to be 195 minus 60 over 9, which is equal to 15. So x is our solution. X equals 15 is our number of x units we should produce. And y is equal to lambda minus 60 over 3. Which is 195 minus 60 over 3, or 45. So what that tells you is that the minimum value, and you can go through and actually classify this as well using the the classification test for the Lagrange function, but that involves classification tests for a function of 3 variables. So I'm going to avoid that for right now. The main idea here is that turns out that this is a minimum value, so the minimum cost c of xy, minimum cost of c of xy, subject to the production constraint x plus y equals 60 is x equals 15, y equals 45. So if we produce 15 units of x and 45 units of y, we minimize the cost while maintaining our production constraint of 60 units. So this is a very powerful procedure. It applies really any time you have some sort of cost you want to minimize, or any time you have a function that you want to minimize or maximize, but you also have a constraint that you have to take care of. Furthermore, right, you consider a more advanced question, a more complicated question. You could say, what happens if the constraint is different? Let's say we increase the constraint by a little bit, or decrease the constraint by a little bit. how is this going to affect the final outcome here? So I'll call this part B. If the first problem, for the first part of this problem, we'll say is just part A. You have some fixed constraint. Part B is, say, a more general problem. You could say, suppose x plus y equals t, where t is a new production quota. What's going to change here? In part A, t was equal to 60. But what happens if t is a different value than 60, if we sort of increase it a little bit or decrease it a little bit? And what happens is the following. We still have our Lagrange function, but the Lagrange function becomes a function of t and still of all the other variables as well. So x, y, and lambda. And what also is a function is actually x, y, and lambda are functions of t. Right? Assuming we have that value of t, we can go through and do the Lagrange multiplier method, just like we did before with our Lagrange function. But the idea is that the Lagrange function, right, is now going to depend directly on, just like it did before, x, on y, and on lambda, but it also depends on t, because the Lagrange function is going to be the cost function minus our constraint function, which is our lambda times our constraint function, minus this new value, this new production quota. So say for a fixed value of t, you can actually go through, just like we did before. For any value of t, we can go through and directly solve I'll say that go through the same procedure as in A, which means we go through and we solve df dx equals 0, df dy equals 0, and df d lambda equals 0, and solve for x, y, and lambda, just like we did before, but these are going to depend on that new production constraint, t. Or another way of saying that is that there are functions of t. So let's say we do that. We go through and we get x of t, y of t, and lambda of t, such that the x partial derivative at this r of t equals 0, the y partial derivative r of t is equal to 0, and the z partial derivative is equal to 0. And not only that, we'll call the minimum value, which is the minimum cost, m of t, because that's also going to depend on this new production quota, m of t. Specifically, it'll be the cost function at x of t and y of t, which we know is the same thing as the Lagrange function at x of t, y of t, lambda of t, comma t, because the Lagrange function satisfies that equation 3, which is that the constraint term holds, or g of xy minus t is 0. So we could say, what's the rate of change, or the derivative of this minimum cost, this m of t? And the correct answer to this question lies in the multivariable chain rule, because this minimum cost depends on a number of different things. It depends on t independently. It also depends on x, on y, and on lambda as well. These optimal solutions for x, y, and lambda, which all also depend on t. So from the multivariable chain rule, the rate of change of the minimum cost, m prime, or dm dt, is going to be the partial derivative of f with respect to t plus the partial derivative of f with respect to x times the partial derivative, or the single variable derivative of x with respect to t, plus the partial derivative of f with respect to y times dy dt, plus the partial derivative of f with respect to z times dz dt. Or not z, but lambda, sorry. And you might think, oh wow, this is getting long and complicated. Like, how are we going to figure out all of these things? Could we possibly have enough information to figure out all of these things? And the answer to that question is relatively simple. These partial derivatives, df dx, df dy, and df d lambda, are all 0, because x of t, y of t, and lambda of t all satisfy the condition of the minimum, the fact that it's minimizing this Lagrange function, or it's minimizing the cost subject to our constraint. And because of that, the conditions of the minimizing x of t, y of t, and lambda of t, minimizing and being critical points of our Lagrange function, are exactly that partial derivatives are 0. So this is 0. This is 0. And this is 0. It's guaranteed to be 0 by the sole fact that we ended up going through and solving this system of equations for this specific value of t. Now you could go through and do that, but in general it'd be a little bit complicated. You have to keep track of everything and solving for that. So it's much easier to do it this way, because it kind of completely removes our goal, or not our goal, it removes our the long and complicated and arduous process of going through and solving that system of equations in general for a general production constraint t. And what happens here is that we have the following result. That m prime of t is directly equal to the partial derivative of f with respect to t, which, if we go up and we look at f, the partial derivative of capital F with respect to t is going to be negative lambda times negative 1, or lambda of t times negative 1, which is just equal to lambda of t. So what this is saying is that the rate of change of that minimum, of the minimum cost, is directly equal to the Lagrange multiplier at t, at a given production constraint t, or that dm dt is equal to lambda. This is true for any any Lagrange minimization problem, which is quite amazing that we can do this and get this general relationship. It's very, very, very powerful. What it's saying is that we can use this, right? We know that if, let's say, for instance, we have a small change. So we have a small delta t, or a small change in production quota. Call this delta t. Well, we know from linearization that m of t at a given point close to delta t. The delta t here is t minus t naught, where like t naught, say, is like our initial production quota and t is the new production quota. If delta t is much less than 1, so it's very small, I should say it's small relative to the function, so we'll just say small, then m of t is going to be approximately equal to the minimum value at t naught plus the derivative m prime at t naught times delta t. This is our linearization approximation for a single variable function. And what we've just shown is that this is the same thing as m of t naught plus lambda of t naught times delta t. Or for small delta t, that m of t minus m of t naught, the difference in the minimum at a given production quota t naught in t for small differences is approximately equal to lambda times t naught, or lambda of t naught, the Lagrange multiplier at t naught, times this difference, delta t. So this is a very, very useful thing and useful rule of thumb that can be used to help us figure out, say, how this minimum is going to change without doing much calculation. So for instance, let's say we take our previous problem and we change to a new production quota. Right? In the first problem, or part A of the problem, our production quota was the production quota of 60. We had a production quota of 60, so that's our T naught for part A. So T naught is the production quota from the first part. Let's say we can increase that a little bit. We can go to, say, T naught is equal to 61, say. Or so T, say, our new production quota, we can raise it up to 61 maybe. Right, then the minimum, to use this equation, the minimum at 60, or the minimum at 61, minus the minimum at 60, the difference in minimums between these two problems is going to be approximately equal to our Lagrange multiplier from the first part, which is the Lagrange multiplier corresponding to a production quota of 60, which is 195, multiplied by 61 minus 60, or 1. Right, and so approximately speaking, the minimum is gonna increase, but the difference in the minimum at the production quota of 60 and the minimum at a production quota of 61 is going to be 195 approximately. it's not an exact equation because whenever you're doing a derivative approximation, you always have some error. But the idea is that we can directly use this and do this process. And we can do it very quickly. Right? We don't have to go through and actually solve the new problem for that new production quota, which is very, very useful. But that'll do it for the lecture today. Thank you very much for tuning in, and I hope you learned something. Have a great day.